y'all. If you are joining me after the volumetric stoichiometry video, then you are in the right place. We are going to be looking at the second half of our Day 4 Unit 9 notes in this video. So we're going to be talking about calculating percent yield. As you can see, we have our percent yield equation right here. And not to worry, you don't have to memorize this equation. If you go over to your formula chart on your periodic table, you'll see that your percent yield equation is listed right here. So you can refer to that anytime you want. It's actually on the same page as your molar volume conversion. So those are nice and neat in one place. So refer to that anytime you need it. If you are asked for percent yield, you will need that equation. So before I actually start this example, we are going to talk a little bit about the parts of the percent yield equation. You'll see that percent yield is equal to actual over theoretical times 100. What that means is the number that you would put up here in actual. We have a little explanation for actual and theoretical. The actual amount that we would put right here is how much we made actually in our lab, for example. If you were to do this reaction in a lab, the actual amount is what you got when you did this reaction in the real world. On the bottom, we have the theoretical amount. The theoretical is the value that you get from your stoichiometry calculations. So when you're doing your dimensional analysis, when you calculate how much you should actually get, if everything went perfectly, that is your theoretical. So you're going to get this theoretical from doing your calculations. The actual, we would give this to you in your word problem. So you would need to be able to differentiate between the two, what those words mean. Another way we can look at this is that the percent yield is equal to the value that we get in the lab over the value we get by doing our stoichiometry times 100. So again, that's still actual over theoretical. These are just some keywords that you might see associated with the actual and with the theoretical. So now that we've talked a little bit about that equation, I want to go ahead and do this example with you. The first part of this example is going to have us do some dimensional analysis, some stoichiometry, in order to get our theoretical. So you'll see right here we have using 13.7 moles of aluminum, how many grams of aluminum oxide should we produce? So this should we produce, this is telling me how much should we theoretically produce, right? So I like to underline my important words and phrases and numbers. Right here, I'm told that my given is 13.7 moles of aluminum, and we want to calculate how many grams of aluminum oxide we should get. So before we can do this, we need to make sure we have a balanced equation. Remember, on your quiz and test, you will be given the skeleton equation. You need to be able to balance this. So if you want to get some more practice balancing, go ahead and pause me real quick. I'm going to fill in the numbers in a second here. Okay. So if you are unpausing me now to check your work, the numbers you should have gotten to fill in to balance this equation are 4, 3, and 2. This is a balanced equation. I'm going to go ahead and rewrite this balanced equation down here so I can make myself a stoichiometry map. So I see I have 4 moles of aluminum, 3 moles of oxygen, reacting to form 2 moles of aluminum oxide. So there is my balanced equation. I want to make a map here so I know how to set up my dimensional analysis. I'm told that we have 13.7 moles of aluminum, and we want to figure out how many grams of aluminum oxide we need. So we're going from moles to grams. So I can't go directly from moles to grams, but I can go from moles to moles. So I can convert between moles of substances in my reaction. So I'm going to draw myself an arrow over here because I want to convert from moles of aluminum to moles of aluminum oxide. And again, to do that, we're going to use our handy-dandy mole ratio. In other words, we're going to need our coefficients, these big numbers in front of our elements in our compounds, to convert. And once we are in moles of aluminum oxide, we can convert from moles of aluminum oxide to grams of aluminum oxide using, you guessed it, molar mass. So I'm going to make myself a note there so I remember that I need molar mass. So we're going to go ahead and set up our dimensional analysis. Again, we're going to write our given first. We're going to write number, unit, and substance. We have 13.7 moles of aluminum. We want to make sure we're being specific. We want to convert moles of aluminum to moles of aluminum oxide. So again, we're going to take this unit. What goes up must come down. Put this unit here. And then we're going to convert to moles of aluminum oxide. It's great that I drew myself a map because I know exactly where I am going. So I see that the number 4 is associated with aluminum, so I get to put that right here. 4 moles of aluminum will react to form 2 moles of aluminum oxide. So at this point, we have taken care of this arrow. Remember, the number of arrows that we draw represents the number of steps in our dimensional analysis. So we've done the first step. Our moles of aluminum will cancel out and leave us with moles of aluminum oxide. So now we want to convert moles of aluminum oxide to grams of aluminum oxide. In order to do that, we wrote that we needed the molar mass. So I'm going to make myself some space to show my work so I can go ahead and calculate that molar mass. So molar mass of aluminum, we have 2 atoms of aluminum, and we have 3 oxygen. So I'm going to come over to my periodic table and grab my average atomic mass of aluminum, 26.98. We're going to have to do that times 2. And oxygen, my average atomic mass, is 16. So if you want to practice typing this into your calculator, you can. In the end, you're going to get 53.96 plus 48 for a total of 101.96 grams per mole. So we have calculated our molar mass. We can go ahead and plug this in. There are 101.96 grams of aluminum oxide in 1 mole of aluminum oxide. So we have made it to grams. We will cancel out our moles of aluminum oxide and be left with grams of aluminum oxide. So now I'm going to go ahead and type that into my calculator. 13.7 times 2 times 101.96. And then we're going to divide that by 4, because 4 is on the bottom. We get 698.426. But remember that right here, we were given a number with 3 significant figures. So I want you to make sure that you round this to 3 significant figures as well. 698 grams of aluminum oxide. So we should produce, theoretically, in a perfect world, we should produce 698 grams of aluminum oxide. So I'm going to keep that in mind. I'm going to move my paper. I wanted to write this extra big for y'all. But I'm going to keep in mind that I should produce this much in a perfect world, because we're going to use this theoretical, to help us calculate the percent yield. Because part B of this problem asks us, what is the percent yield if we actually produced 601.4 grams of aluminum oxide? So remember, our percent yield equation, we wrote it right up top, so I'm going to write it again down here, is actual over theoretical times 100. Okay? So now I'm just going to plug in my numbers. We said we're going to actually produce 601.4 grams of aluminum oxide. But theoretically, If our reaction had went perfectly, we should have gotten 698 grams of aluminum oxide. Do that times 100. If we put this into our calculator, 601.4 divided by 698, multiply it times 100, you should get 86.16, or you can round it to, if we round it to 3 sig figs here, percent. So that is our percent yield. Our reaction was 86.2% efficient. It was pretty efficient. Now that we have done this practice problem together, what I want you to do is go ahead and flip to the back page of your notes and try the day 4 practice problems.